Makemake stands as one of the most significant dwarf planets in our solar system, occupying a distinctive position in the cold, distant reaches beyond Neptune. As the fourth largest dwarf planet discovered to date, Makemake provides astronomers with valuable insights into the structure and composition of the outer solar system. Its location, orbital characteristics, and physical properties are directly influenced by its position far from the Sun. This distance shapes everything from its surface composition to its temperature and even its classification within our planetary system. Makemake's position not only defines its own characteristics, but also helps scientists better understand the broader architecture of our cosmic neighborhood. Makemake was discovered on March 31, 2005, by a team led by Michael E. Brown, and was officially announced on July 29, 2005. Initially designated as 2005 FY9, it received its permanent name in July 2008, derived from the creator deity of the Rapa Nui people of Easter Island. The discovery of Makemake occurred during a period of intense exploration of the outer solar system, which also yielded other significant dwarf planets including Eris and Haumea. Makemake is classified as a dwarf planet, which is essentially a miniature version of a planet like Earth. It belongs to a select group of celestial bodies that meet the criteria for dwarf planet status. It orbits the Sun, has sufficient mass for its gravity to pull it into a roughly spherical shape, has not cleared its orbital neighborhood of other material, and is not a satellite of another planet. This classification places Makemake in the same category as Pluto, Ceres, Haumea, and Eris. Within the broader classification system of solar system objects, Makemake is specifically identified as a classical Kuiper Belt Object, KBO. The classical KBO designation indicates that its orbit lies far enough from Neptune to remain stable over the age of the solar system, distinguishing it from other types of Trans-Neptunian objects whose orbits are significantly influenced by Neptune's gravity. This positional stability makes Makemake particularly valuable for studying the primordial conditions of the outer solar system. Makemake is further subcategorized as a dynamically hot classical KBO due to its high orbital inclination of nearly 29 degrees. This means its orbit is significantly tilted relative to the ecliptic plane, the plane containing Earth's orbit around the Sun. This classification offers clues about Makemake's formation and evolutionary history, suggesting it may have experienced significant gravitational interactions in the past that altered its orbital plane. Makemake's orbit defines its position in the solar system and distinguishes it from other celestial bodies. The dwarf planet follows an elliptical path around the Sun with a semi-major axis of 45.430 astronomical units, AU. This means that, on average, Makemake is positioned about 45.430 times farther from the Sun than Earth, or approximately 6.8 billion kilometers away. This vast distance places Makemake firmly in the outer reaches of our solar system, far beyond the orbit of Neptune. The eccentricity of Makemake's orbit is 0.1126, which represents a moderate level of ellipticity. This orbital characteristic causes Makemake's distance from the Sun to vary considerably throughout its journey. At perihelion, its closest approach to the Sun, Makemake comes within 38,104 AU of our star. At aphelion, its most distant point, it reaches out to 52.756 AU from the Sun. This variation in distance affects the amount of solar radiation Makemake receives, influencing its surface temperature and the behavior of volatile ices on its surface. One of the most distinctive aspects of Makemake's position is its orbital inclination of 28.9835 degrees, often rounded to 29 degrees. This high inclination means that Makemake's orbit is tilted significantly relative to the ecliptic plane. As a result, Makemake spends much of its orbital period well above or below the plane in which most planets orbit, following a path through space that differs markedly from the inner planets. This inclined position affects when and where Makemake appears in Earth's sky, and contributes to its classification as a dynamically hot classical KBO. Makemake completes one full orbit around the Sun in approximately 306.21 years. This extended orbital period is a direct consequence of its distant position. For comparison, Earth takes just 1 year to orbit the Sun, while Pluto requires 248 years and Haumea needs 283 years. Makemake's long orbital period means that it moves very slowly through the zodiacal constellations as viewed from Earth, taking decades to traverse a single constellation. As of April 2019, Makemake was positioned at about 52.5 AU from the Sun, placing it near its aphelion. The dwarf planet will reach its aphelion in 2033, after which it will begin its long journey back toward the inner solar system. Makemake is not expected to reach perihelion again until November 2186, highlighting the vast timescales involved in the orbital dynamics of distant solar system objects. Interestingly, Makemake is positioned near the 13.7 resonance with Neptune, though this appears to be coincidental rather than the result of evolutionary dynamics. Unlike resonant KBOs, such as Plutinos, that have a 2.3 resonance with Neptune, Makemake's orbit is sufficiently distant to avoid significant gravitational perturbations from the ice giant, contributing to its classification as a classical KBO. Makemake resides in the Kuiper Belt, a disc-shaped region that extends from approximately 30 AU, the orbit of Neptune, to about 50 AU from the Sun. This vast ring of icy bodies encircles our solar system beyond Neptune and contains numerous objects ranging from small frozen debris to large dwarf planets. The Kuiper Belt is of particular interest to astronomers because it preserves material from the early solar system, offering a glimpse into the conditions that existed when planets were forming. Within the Kuiper Belt, Makemake is positioned as one of the largest and most significant objects. It ranks as the fourth largest dwarf planet in the solar system, with a diameter of approximately 1,430 kilometers. This substantial size, combined with its highly reflective surface, makes Makemake the second brightest Kuiper Belt object after Pluto, despite its extreme distance from both the Sun and Earth. Makemake's specific location within the Kuiper Belt places it in what astronomers call the classical Kuiper Belt. Classical KBOs have orbits that are relatively stable and not in significant resonance with Neptune. Their orbital paths keep them far enough from Neptune to avoid strong gravitational interactions, allowing them to maintain consistent orbits over billions of years. This positional stability makes Makemake and other classical KBOs valuable for studying the primordial outer solar system. As a dynamically hot classical KBO, Makemake belongs to a subpopulation characterized by higher orbital inclinations and eccentricities. This contrasts with the dynamically cold population that orbits closer to the ecliptic plane with more circular orbits. The position of Makemake in this hot population suggests it may have experienced significant gravitational scattering events in the past that altered its orbital plane, potentially providing clues about major dynamical changes in the early solar system. Makemake's position within the classical Kuiper Belt also places it at a distance where solar radiation is significantly reduced compared to the inner solar system. At approximately 45.8 AU from the Sun, Makemake receives only about 1/2000th of the solar energy that reaches Earth. This minimal solar heating contributes to Makemake's extremely low average temperature of about 40 Kelvin, 233 degrees Celsius. These frigid conditions allow volatile compounds like methane, ethane, and possibly nitrogen to exist as solid ices on Makemake's surface, directly linking its positional characteristics to its physical properties. Makemake's position can be better understood by comparing it with other significant bodies in our solar system. Among the recognized dwarf planets, Makemake occupies an intermediate position in terms of distance from the Sun. Ceres, the innermost dwarf planet, orbits within the asteroid belt between Mars and Jupiter at approximately 2.8 AU. Pluto maintains an average distance of about 39.5 AU from the Sun, somewhat closer than Makemake. Haumea follows an orbit similar to Makemake's but is slightly closer to the Sun with a semi-major axis of about 43 AU. Eris, the most distant known dwarf planet, orbits at an average distance of about 68 AU. Makemake stands as the second farthest dwarf planet from the Sun, with only Eris orbiting at a greater distance. This positioning places Makemake in a region where solar radiation is dramatically reduced compared to the inner solar system, significantly affecting its surface temperature and composition. The extreme distance also results in a substantial light travel time, with sunlight taking approximately 7 hours and 22 minutes to reach Makemake. This means that if the sun were to hypothetically disappear, an observer on Makemake wouldn't notice for more than 7 hours. In relation to the 8 recognized planets, Makemake orbits far beyond Neptune, the outermost planet. Neptune orbits at an average distance of 30.1 AU from the Sun, placing Makemake more than 15 AU farther out. This substantial distance beyond Neptune's orbit defines Makemake as a Trans-Neptunian object, TNO, a category that includes all bodies orbiting the Sun at greater average distances than Neptune. From Earth's perspective, Makemake's position varies considerably due to the combined orbital motions of both bodies. On average, Makemake is located about 53.2 AU from Earth, though this distance fluctuates as both bodies move along their respective orbits. This vast separation affects how easily astronomers can observe the dwarf planet, with optimal viewing conditions occurring when Makemake is at opposition, when Earth is between the Sun and Makemake. When considering orbital paths rather than just distances, Makemake's orbit shows interesting similarities to that of Haumea, another dwarf planet in the Kuiper Belt. Both follow highly inclined orbits with moderate eccentricities, though Makemake's orbit is slightly farther from the Sun in terms of both semi-major axis and perihelion. These similarities may provide clues about shared formation or evolutionary processes in this region of the solar system. Makemake's distant position in the solar system significantly influences how it can be observed from Earth. Despite being located at such extreme distances, Makemake is visually the second brightest Kuiper Belt object after Pluto, with an apparent magnitude of approximately 17.0 at opposition. This relative brightness results from a combination of its substantial size and highly reflective surface, which has a geometric albedo of 0.82 plus 0.02, meaning it reflects about 82% of the sunlight that reaches it. The brightness of Makemake from Earth's perspective fluctuates based on its changing position relative to Earth. When Makemake is at opposition, when Earth is positioned between the Sun and Makemake, it appears at its brightest because it is fully illuminated from our vantage point. Conversely, when it is in conjunction, on the opposite side of the Sun from Earth, it appears dimmer and is more challenging to observe. Despite these variations, Makemake remains bright enough to be visible using high-end amateur telescopes under good viewing conditions. Makemake's current position has it traveling through the constellation Coma Berenices, though this will gradually change over time due to its orbital motion. According to the search results, Makemake will pass from Coma Berenices to Boötes in November 2028. This slow apparent motion across our sky is a direct consequence of Makemake's distant position and long orbital period. For observers on Earth, this means that Makemake remains in the same general area of the night sky for many years. The extreme distance of Makemake also affects the level of detail that can be discerned through direct observation. Even with powerful telescopes, Makemake appears as little more than a point of light from Earth. Determining its size, shape, and surface features requires indirect methods such as stellar occultations, when Makemake passes in front of a star, temporarily blocking its light, and observations across multiple wavelengths. In 2011, a stellar occultation by Makemake provided valuable data that helped establish its dimensions at approximately 1,434 x 1,420 kilometers. Light travel time is another important observational aspect resulting from Makemake's position. The light we see from Makemake takes approximately 7 hours and 22 minutes to reach Earth, meaning we always observe the dwarf planet as it was more than 7 hours in the past. This light travel time must be accounted for in precise astronomical measurements, and when planning observations that depend on exact timing, such as occultations. Makemake's distant position from the Sun has profound effects on its physical characteristics, particularly its surface composition and temperature. Located at an average distance of about 45.8 AU from the Sun, Makemake receives significantly less solar radiation than the inner planets. This reduced solar heating results in an extremely cold surface, with temperatures estimated to be around 40 Kelvin, approximately 233 degrees Celsius. These frigid temperatures, a direct consequence of Makemake's position, allow volatile compounds that would vaporize closer to the Sun to exist as solid ices on the dwarf planet's surface. Spectroscopic observations indicate that Makemake's surface is covered with methane, ethane, and possibly nitrogen ices. The presence of these ices is directly related to Makemake's position in the cold outer regions of the solar system, where these compounds can remain stable in solid form for billions of years. The composition of these surface ices also suggests that Makemake's position has remained relatively stable over long periods. If Makemake had migrated significantly closer to the Sun at any point in its history, these volatile ices would likely have sublimated and been lost to space. The preservation of these materials provides evidence that Makemake has maintained its distant position for much of the solar system's history. Makemake's position also influences its day-night cycle. With a rotation period of approximately 22.83 hours, a day on Makemake is slightly shorter than an Earth day. However, due to its distant position, the intensity of sunlight during Makemake's day is drastically reduced compared to Earth. At Makemake's distance, the Sun would appear as little more than a very bright star, providing minimal warming effect to its surface. Interestingly, despite the extreme cold at Makemake's position, there are indications of potential geothermal activity. According to the search results, Makemake shows signs of geothermal activity and might harbor an active subsurface ocean. If confirmed, this would suggest that Makemake's internal heat, possibly generated by radioactive decay within its rocky core, is sufficient to maintain liquid water despite the dwarf planet's distant position from the Sun. The high reflectivity of Makemake's surface, with a geometric albedo of 0.82 plus 0.02, is also indirectly related to its position. This high albedo suggests a fresh, clean surface covered in reflective ices. In the inner solar system, such volatile ices would sublimate away, but Makemake's distant position preserves them. This reflective surface contributes to Makemake's relative brightness as observed from Earth, making it more readily observable despite its extreme distance. Makemake's position in the solar system extends beyond the dwarf planet itself to include its satellite system. In 2016, astronomers announced the discovery of a moon orbiting Makemake, provisionally designated S 2015-136472-1 and nicknamed MK2. This discovery added Makemake to the list of dwarf planets known to have natural satellites, joining Pluto, Haumea, and Eris. The moon's orbital configuration is particularly interesting from a positional perspective. MK2 orbits Makemake in a nearly edge-on configuration when viewed from Earth. This edge-on orientation made the moon difficult to detect, as it spent much of its orbit hidden within the glare of Makemake. According to the search results, MK2 is very dark, approximately 1/300 times fainter than Makemake itself, further complicating its detection. The discovery of MK2 provides valuable information about Makemake's position in the broader context of Kuiper Belt, object formation and evolution. Many large KBOs, including all of the other officially recognized dwarf planets in the Kuiper Belt, have satellites. The presence of MK2 suggests that whatever processes led to satellite formation in the outer solar system also occurred at Makemake's position. MK2 is relatively small compared to its parent body, with an estimated width of less than 100 miles, approximately 160 kilometers, while Makemake itself has a diameter of about 870 miles, 1,400 kilometers. The stark contrast between MK2's dark surface and Makemake's highly reflective one suggests they may have different compositions despite sharing the same position in the solar system. The edge-on orbital configuration of MK2 as viewed from Earth also provides insights into Makemake's orientation in space. Since natural satellites typically form or evolve to orbit near their parent body's equatorial plane due to tidal forces, the edge-on appearance of MK2's orbit suggests that Makemake is being viewed approximately equator-on from Earth. This orientation is consistent with the dwarf planet's small light curve amplitude of only 0.03 magnitudes. The presence of a satellite also allows astronomers to eventually determine Makemake's mass through observations of the moon's orbital period and distance. This information, currently unavailable for Makemake, would provide additional insights into the dwarf planet's density and composition, further enhancing our understanding of its position in the evolutionary history of the outer solar system. Makemake's position in the outer solar system makes it a scientifically valuable object for several reasons. As one of the largest bodies in the Kuiper Belt, its physical and orbital characteristics provide important constraints for models of solar system formation and evolution. Its current position is likely the result of billions of years of gravitational interactions, preserving information about the dynamic history of our planetary system. The position of Makemake beyond Neptune places it in a region where primordial material from the solar system's formation has been preserved in a relatively pristine state. The extremely low temperatures at this distance have allowed volatile compounds to remain frozen on Makemake's surface, providing a window into the composition of the material from which the planets formed. This makes Makemake's position particularly valuable for understanding the distribution of elements and compounds in the early solar system. Makemake's position as a dynamically hot classical KBO also offers clues about past gravitational disturbances in the outer solar system. Its high orbital inclination suggests it may have been scattered from a different original position, potentially by the migration of the giant planets early in solar system history. By studying objects like Makemake, astronomers can reconstruct the complex gravitational interactions that shaped our planetary system. From an observational standpoint, Makemake's position makes it one of the most accessible large Kuiper Belt objects. Despite its extreme distance, its size and high albedo make it bright enough to observe with advanced amateur equipment, allowing for widespread study by the astronomical community. This accessibility has facilitated detailed investigations of its rotational period, surface properties, and even the detection of its moon, all of which enhance our understanding of distant solar system bodies. The position of Makemake in the classical Kuiper Belt also makes it an important reference point for understanding the population distribution in this region. By comparing Makemake with other Kuiper Belt objects at different distances and inclinations, astronomers can map the structure of this region and identify patterns that reveal the processes that shaped it. This contributes to our broader understanding of how planetary systems form and evolve. Makemake's position in the solar system represents a critical element in our understanding of the outer reaches of our cosmic neighborhood. As one of the largest classical Kuiper Belt objects and the second farthest recognized dwarf planet from the Sun, Makemake exists in a region that provides valuable insights into the conditions and processes that shaped our solar system. The dwarf planet's orbital characteristics, including its semi-major axis of 45.430 AU, eccentricity of 0.16126, inclination of nearly 29 degrees, and orbital period of 306.21 years, define its position within the classical Kuiper Belt population. This position places it beyond the significant gravitational influence of Neptune, allowing it to maintain a relatively stable orbit over billions of years. Its current journey toward aphelion in 2033, followed by a gradual return to perihelion in 2186, serves as a reminder of the vast timescales that characterize the dynamics of the outer solar system. Makemake's distant position directly influences its physical properties, most notably its extremely low temperature and ice-covered surface. The dwarf planet's high albedo and distinctive spectral signature result from a surface rich in methane, ethane, and possibly nitrogen ices, compounds that can only remain stable as solids in the cold conditions found at Makemake's distant position. These characteristics not only define Makemake's nature, but also provide valuable data about the conditions and composition of the outer solar system. The discovery of Makemake's moon, MK2, adds another dimension to our understanding of the dwarf planet's position, suggesting that satellite formation processes were active throughout the outer solar system. The edge-on configuration of MK2's orbit as viewed from Earth provides additional context for Makemake's orientation in space, while the stark contrast between the moon's dark surface and Makemake's bright one raises interesting questions about compositional differences even at the same position in the solar system. As our knowledge of the solar system continues to evolve, Makemake's position remains a valuable reference point for understanding the distribution of mass, the processes of planetary formation, and the conditions that exist in the cold outer regions beyond Neptune. Its study continues to yield new insights into our cosmic neighborhood, reminding us that even in the most distant reaches of our solar system, there are worlds with their own unique characteristics and stories to tell.